Picture what happens when you turn a key and hit the gas. You are taking a metal box weighing several tons and hurling it over uneven ground at highway speeds, propelled by thousands of controlled, violent explosions happening every single minute. If you were to take that exploding engine block and bolt it directly to four wheels, the raw force would be unusable. The vibrations would shake the entire contraption apart within seconds. To manage that energy, modern automobiles are constructed from 6 distinct, specialized engineering subsystems. Each one is designed to isolate and direct specific forces before they reach the driver. To understand how a car works, you have to look past the exterior and observe how these individual components solve the physical challenges of the road. This image shows the first necessary solution, a rigid skeleton. Before any movement can occur, you need a heavy-duty structure to hold human cargo and provide a stable mounting point for the mechanical components. Older off-road vehicles rely on a body-on-frame design, where the passenger cabin is dropped onto a separate steel ladder. Most modern cars use a unibody construction, which combines the frame and the body panels into a single structural shell. Look at this 1950s assembly line. For a century, the auto industry has been built around the logistical challenge of mass-producing these heavy structural supports. The body and frame act as a safe stage. It sits inert, waiting for the active, violent systems to be bolted onto it. To push that heavy stage forward, you must generate massive force. For over 100 years, that task fell to the internal combustion engine. Inside the engine block, the 4-stroke cycle happens continuously: intake, compression, power, and exhaust. These vertical thrusts push a crankshaft, turning up and down motion into rotational torque, which is captured by a heavy flywheel to smooth out the spin. While an internal combustion engine relies on detonating gasoline or diesel fuel, electric and hybrid motors perform this same mechanical role using battery power. The engine's purpose is containment. It isolates chemical reactions and funnels them out as a single stream of mechanical energy. An engine spins far too fast to connect directly to a set of wheels. You need a mediator to step in and manage rotational speed. That mediator is the transmission. In a manual gearbox, the driver selects the gear ratios. In an automatic, the driver selects a travel mode and the system shifts itself. In a front-wheel drive setup, the clutch, gearbox, and differential are packed into one front housing. In rear or all-wheel drive, a long propeller shaft runs down the chassis, carrying torque to power the rear or both axles. Together, the engine and transmission form the powertrain. This system acts as a mechanical translator, turning engine speed into precise wheel rotation. If a rigid frame rested directly on metal axles, the upward impact from every rock and pothole would quickly shatter the vehicle. This image shows the mechanical buffer zone, the suspension. Engineers use McPherson struts, coil springs, and shock absorbers to absorb and dissipate kinetic shock away from the cabin. The final protection comes from tires. These flexible rubber chambers wrap around the wheels, acting as the only physical contact point with the ground. The suspension's purpose isn't just passenger comfort. Its real job is ensuring the tires stay pressed against the pavement to maintain traction. We have a frame, an engine, a transmission, and a stabilized suspension. Now, a human has to tame and direct this moving machinery. Steering translates the turn of a wheel into directional movement at the front axle, while braking systems scrub off speed to hold the machine still. Tying these systems together is an electrical nervous system. Powered by a battery and generator, a web of wiring feeds electricity to components ranging from the starter motor to the headlights. These electrical and manual controls form the bridge between human intent and mechanical execution. When you look at these systems in isolation, they are complex metal puzzles. But when properly assembled, they depend entirely on one another. The engine is useless without the transmission to route its power. The frame cannot travel without the suspension to float it over the ground. And none of it functions without electrical command holding the logic together. Looking back at early iterations, like this turn-of-the-century test vehicle, you can see the basic DNA was established early on. But comparing that open carriage to a dense architecture of today, highlights the scale of modern engineering evolution. Shifting into drive engages 6 distinct engineering disciplines at once. It places the driver at the center of a system, where every mechanical pulse is synchronized to the needs of the road.